Hello. In this lecture, we're going to study and try to understand certain models called the kinetic models, or to understand or to define systems. Especially, we will, as an application, we will be discussing the SIR model, which is basically a more advanced model that, for understanding or modeling the outbreaks than what we have seen in the previous lecture. If just to remember what we have just talked about, the outbreak model, to understand the first or the initial phases of the outbreak, we assume that the population is homogeneous, and it starts with a single or with a certain number of infected individuals. And these individuals are randomly encountering other people, and the number of these peoples are denoted by E, and every day. And with a certain probability, these encounters ended with transmission of the disease. And new infected individuals are created. So every individual, new individual, also encounters a certain group of people, and new cases are created. The average number of people, E, and the probability of transmission, P, is average numbers. So as the population is homogeneous, on average, every day, these numbers are the same. But as you can see from this definition, the number of new cases each day on the left-hand side at the bottom corner, you can see that the number of new cases caused every day by a single individual is E times P, which we gave the name K. This K parameter is important because each day the cumulative number of cases for that day equals to the number of cases on the previous day times this number K plus 1. The reasons for this we have just discussed in the first lecture. This tells us that the growth of this n number, the cumulative cases, is exponential, or a geometric series. We learned that it's almost the same thing. However, this K parameter does not stay the same, or it's not a constant, because as the outbreak progresses, the number of infected cases increase. So even if the average encounter of a sick person, of a infected person, is the same E every day, most of these encounters will not result with an infection, because the people this infected person encountered is already had the disease. So the number of new cases each day created by this individual or a single individual start to decrease. The K start to decrease. It should decrease. As you can see now, the every day the new added cases will decrease, so it won't be an exponential anymore. We use a type of function called the logistic function, to incorporate this property into our mathematical model. What we did was we assumed that the K, the value of the K parameter, is dependent on the cumulative number of cases. As the cumulative number of cases increases, the K decreases, and it decreases to at the end to 0, which creates this sigmoid curve for the cumulative cases. The first part of the outbreak represented by an exponential growth, then the growth starts to slow down, you enter a linear phase, then it goes to saturation, where the cumulative number of cases do not increase anymore. K plus 1 goes to 1, K goes to 0. The yellow curve is the K plus 1 parameter, which goes to 1. In this case, at the end, starts from any number and then goes to 1. The bars represent the new cases that is added to the cumulative, which is, in a sense, the derivative of the function. Also, the derivative of the function first increases exponentially, as we know that the derivative of an exponential function is also an exponential function. However, as the k starts to decline or starts to go down, this exponential growth for the derivative does not hold. It comes to a peak value, then it starts to decline. However, this logistic function, it is not a precise definition of a mathematical definition of what's going on, because we said that yes, the k value of the parameter k is dependent on the cumulative number of cases. As the cumulative number of cases increases, the number of k the value of k, the parameter k, should decrease. But what is the relation between them is not precisely defined. It can be anything. Logistic function, in that case, is not a good model, does not specify precisely the relation between the cumulative number of cases and k. There is also other effects we have to consider. For example, like quarantine or mandatory usage of masks in the public, or restrictions of the movements in the population, things like that, which eventually changes the k. And also we have to incorporate these effects on the dynamics of the outbreak, the growth of the cumulative number of cases, how they will be affected by such interventions. So we need a more precise model. So this more precise model, even though it's still a little bit crude, better model than we already have, it's called the SIR model. SIR means that the S means the susceptible population, I means the infected population, the R means the recovered population. What does these mean? What does these mean? The susceptible population mean that the people in this group can catch the disease, but they're not contagious. The infected population means in the population in this group is infected. They cannot catch the disease anymore. They are already infected, but they are contagious. They can infect other people. The R, the recovered, means that in this subgroup, the people has already recovered from the disease. They are immune, so they cannot be infected again, and they are not infectious. They are not contagious. Of course, the recovered population, optimistically called recovered, the diseased population is also in this subcategory. They cannot be infected, they cannot infect other people. So, as you can see, the transition between these groups is one way. So, susceptible people in the susceptible group can only go to the infected group. The people only in the infected group cannot go back to susceptible group. They can only go to recovered group. And the recovered group, if the outbreak lasts for a short period of time, there is nowhere else to go from the recovered group. Okay? Of course, you can go back to susceptible group if the process takes longer and the recovered immune people start to lose their immunity and start to get susceptible again. However, we consider that this is not the case, and to keep things simple, there is the final or the end stage is the recovered group. So, how do they transit from one population to the other population? We call these subgroups the compartments. So this is a compartmental model. Compartmental models can also be used for other to describe other phenomena, especially the pharmacokinetic behavior of drugs and things like that. So the rate of change, the decrease in this case, in the S population, the derivative of this change, ds over dt, it's called, is proportional to the number of people in the in that group, the S denoted by S, and times the number of infected people. And there is an alpha, a factor, which depends on the ENP, actually the rate of encounter between the people in that population, how mobile is the population, and also what is the probability of transmission after each encounter. Decrease in the S means the number of people get infected per unit time. As they go to infected population, the number of susceptible population decreases the same amount. I mean, the number of people who got infected is the number of people that the susceptible population decreased. Because there's nowhere else they can go. So why this rate of decrease or rate of infection is dependent on both S and I? It's very simple, because the transmission can only occur if an infected and susceptible person has an encounter. So this depends on two things. Besides how well the population is mixed, or what is the mobility of population, it depends on how many people in the population. More people, more encounters, and how many infected people there are. More infected people, more encounters that may cause infection. And of course, alpha also tells you there may be many people in the population which are infected and which are susceptible, but they can be immobile. They can be locked down in their houses, so there will be no encounters. So there's another factor, which is alpha, which tells you how well the population is mixing, which means the mobility of the population. And also, again, if everybody wears a mask and they're very cautious about social distancing and things like that, then even though the population is quite mobile, the infection rate, and also even if the number of susceptible and infected people are high, the number of infections will be low, and even can be zero. So alpha in itself is dependent on how well the mixing is within the population. I mean, how many encounters occurring every day, and also what is the probability of transmission in these encounters. So alpha tells us this. So these three parameters, alpha, S, and I, determines the rate of infection, which means that determines the rate of decrease in the susceptible population. So what is the change in the number of infected people? It does not have to decrease. The S has to decrease because there's only people going out of S. Either it will stay the same or it will decrease. There's no other way. But for I, the infected people population, or the compartment, there are two arrows, one going in, one going out. So it can either increase or it either decrease. So the derivative of di over dt can be positive or negative. And first of all, what is the amount of people coming into I? they are coming from S. So the S over dt is the incoming population per unit time. Alpha times S times I is the incoming population. What is the outgoing population? People recovered from the disease are leaving the infected population, infected compartment. So it's dependent on two things. One, how many infected people there are, because more the people are, the more recovery per unit time, as you can understand. If there are less people, then less recovery per unit time. And there's also another factor, beta. Beta is dependent on how long the infection takes. It can take very short periods of time. You can recover it in a few days, or it takes months to recover. So beta determines that. Beta is not dependent on alpha. And also the outflow from the infected population or the infected group, infected compartment, is not dependent on S. It only is dependent on I, the number of infected people. Okay. However, the income dependent on both S and I. And then there is the R population. The R population is the change in the R population can only be an increase. There's nowhere else they can go. There's only an incoming population from I. And then the rate of change for that population is exactly the rate of decrease in the I population, because the people who are recovered leaves the I and gets into the R. So it equals to beta times I. And you have to understand that the number of people in the S, the number of people in I, and the number of people in the R compartments, the sum of these numbers is a constant. Even if people are dying, the number of population at the beginning of the outbreak is the same at any point in time. Some of them can be deceased. However, when you add the numbers, you'll find that the number is the same with the number it's at the beginning of the outbreak. People do not disappear or appear. Of course, if it takes a very long time, like what we are going through now for years, then the population will change. Of course, new people will come into the population, and people will die because of other reasons. Then this does not hold. For short periods of time, actually, outbreaks should last a few months, not years like this. Then this S, I, and R, sum of these being a constant, should hold. Okay, the idea is that if we know the differentials or the derivative functions, what are the functions themselves? What is the function of S? What is the function of I? What's the function of R? The number of population in these groups in respect to time. That's what we're trying to find. If you solve these equations, then you'll find that the susceptible population will decrease, and the infected population will increase for a while, then start to decrease, and the recovered population will always increase, and they'll come to a saturating point. Susceptibles do not have to decrease to zero. Here in this example, it decreased to zero, but it doesn't have to decrease to zero. We'll talk about it later. But the thing is, you usually do not see the whole picture. You usually see something at the middle of the process. You have a certain number of susceptible people, a kinetic of the number of these people, the infected people and the recovered people. The question is, where will it go? How the infection, the number of infected people, will act, behave. You have to understand one thing. an important thing. To see what will be the behavior of the infected people. Will it decrease? Will it increase? How fast it will increase? How fast it will decrease? Which means that what will be the future of the outbreak for the next month, for the next week, for the next 2 months, whatever. You have to understand that what it means that if the number of infected people will decrease, it means that di over dt should be negative. If it increases, then it will be positive. If it's at 0, it means that the number of infected people will stay the same. Being positive or negative or 0 depends on what? Depends on this. If you rearrange the right-hand side of the equation, you'll see that I, the number of infected people, times alpha times S minus beta should be positive or negative. Okay? The I cannot be negative. It must always be a positive or 0 number. The number in the parentheses is negative, then di over dt is a negative number, and if it's a positive number. What makes this number in the parentheses a positive number or negative number? As you can see, this ratio denoted R, alpha times S over beta, is what determines sign of di over dt. If R is 1, equal to 1, which means that alpha times S is equal to beta, which means that the expression within the parentheses, the alpha times S minus beta, as alpha S equals to beta, will be 0, which means that di over dt will be 0, because I can only be a positive number or 0. Which means that the number of infected cases will stay the same. Which doesn't mean that the infection stopped, but the number of daily infected people and the number of daily recovered people is equal. So the number of infected people stays the same. They are not the same people though. The people change, but the number stays the same. Okay, if the R is smaller than 1, which means that A times S is smaller than beta, which means that the expression in the parentheses will be a negative number, which means that the derivative of I, di over dt, will be negative, which means that the number of infected cases is decreasing. And if it's larger than 1, which means that the expression in the parentheses will be positive, because A times S will be larger than beta, which means that that expression will be positive, which means that di over dt is a positive number, which means that the number of infected cases will increase. This is not cumulative numbers though. These are the actual numbers, the numbers at that moment of time. Okay. R, by the way, is not the recovered here. R is a parameter which people are talking about, and which you usually hear it as R0. Okay. If you remember that but we talked about the initial phase of the outbreak, we said that it should be an exponential growth. Our crude model assumed that it should be an exponential growth. Is it the case for this model? Yeah, you can see that it is the case for this model, because at the very beginnings of the outbreak, the number of infections, the infected cases, are increasing. However, as this is a very small number, the decrease in the susceptible population is very, very negligible. As an example, if you have a population of 100 million people, then if you say that the number of infected cases goes from 1,000 to 2,000, really does not change the susceptible population. It decreases the susceptible population by 4,000, but I mean, what is compared to 100 million people, 4,000 is really a negligible number. So you can assume for the very beginning of the outbreak, the susceptible number of people, more or less constant. Then you can say that S0, we say it. So all that expression in the parentheses is a constant, alpha times S0, which is a constant, minus beta. So, which means that the derivative of I function, with respect to time, is equals to itself times a constant. Which means that this equation is an exponential equation. Of course, you have to account for that constant, and you put it up in the exponent. That means that for the very beginning of the outbreak, as the number of infected cases is negligible compared to the number of population, or the whole population, the growth of infected people is an exponential. Because there's no recovery here. The recovery does not kick in yet. There's not enough time for the recovery to occur. And also the number of infected people, even though increases, does not change the susceptible population significantly. Okay. So our crude model holds for the very beginning of the outbreak. However, as time progresses, as outbreak progresses, the number of susceptible people will decrease, and also there will be recovery, so it won't be the increase in the infected people, number of infected people will not be an exponential. So we talked about some precautions. What are the effects of those precautions? We talked about mask usage or social distancing, things like that. It decreases the chances of encounter, and it decreases the chances of transmission, which decreases alpha. If you talk about the beta, the treatment, if you have one, can decrease the time people stay infected or in the infectious state. For example, for COVID, there is no such treatment we can rely on very much. However, there is one other measure that can increase beta, which is called quarantine. Quarantine means people do not, it doesn't mean that people go from I to R, the compartment I to compartment R, by recovery. However, what you do is you isolate them so they're not recovered, but they become non-infectious quickly. So if you can really be very, very quick, so if someone gets infected and immediately you put them into quarantine, which means that beta is very high, so they will find almost no chance to infect other people. So this is a very effective method to increase beta quarantine, effective quarantining. Okay, as you can easily see that R is dependent on not only alpha and beta, but it also is dependent on the S. S is the susceptible population. Thus, as the outbreak progresses, the S, the susceptible population, will change inevitably. So R is not a constant value. Even if the alpha and beta stays the same, stays constant, which may not, but even if they both stay the same throughout the outbreak, S has to change. So R is not a constant. So this brings us to the question. First of all, there are two definitions. Basal reproduction ratio, which is R0. R here is not the recovered population. R is the constant we are talking about, which is dependent on the S, alpha, and the beta. Unfortunately, there is this confusion shown by a capital R, but they're not the same thing. They're quite different. So we have to understand what basal reproduction ratio is and what is effective reproduction ratio is. One is R0, basal reproduction ratio, and effective reproduction ratio is RT. Second question we have to answer is, what does it mean to be endemic or epidemic? for a contagious disease, and also what does herd immunity mean? We probably hear about this herd immunity thing a lot. Read it on the internet probably. But what does it mean? What I mean is, when I say what does it mean, what I try to ask is, what does it mean in terms of this model, this mathematical model, SIR model? And as you can guess, all these questions is kind of related to this term in the brackets, alpha times S minus B, beta minus beta. So these are 3 questions that you think about, do some research about, and we probably will talk about these in the next live lecture, probably next week. See you.